It's Georgia Weedman, author of Penetration Testing, a hands-on introduction to hacking, and your instructor for this accompanying lab. So we're going to start looking at writing our own exploits, and this first example is actually almost exactly straight from version 1 of Penetration Testing, a hands-on introduction to hacking. I haven't in general gone into a lot of theory with these labs because, well, who wants to watch me for an hour when they just want to see how to get, their things? And, I hope you guys have read the book or are reading the book or will be reading the next book, when we put out the labs for that one. But this one, I do want to show you just a little bit of theory about, how memory works and stuff. So it is chapter 17 of the book, I think. I should know these things. So I just have the book here. So what we're going to do is work with the stack-based buffer overflow. You can think of the stack in memory as kind of like scratch space. So every function that gets called, be it main, be it, my function I created or whatever, or a built-in function like stir copy that we'll see, when they get called, when they're executing, they have space on the stack to store their local variables, do their work that they need to do. And, this is another one of those things that I really wish I'd been in the room to be like, why did you think this was a good idea? So this is a really dumbed down version of, what a program looks like in memory. And the stack, it grows from higher memory addresses to lower memory addresses. Though when data gets copied in, it goes from lower memory to higher memory. So you might get see where this might start to be a problem. Anyway, so when I wrote this 32-bit, but the only difference here really for this example is that this is a 64-bit machine. At this point, there are differences certainly besides the addresses getting twice as long, being, 64-bit instead of 32, so 8 bytes instead of 4. But also the register names, instead of with an E, they're going to start with an R. There are other differences in terms of, exploitation of 64 versus 32, but for now, really just your memory addresses are twice as long, and your register names are going to start with an R instead of an E. The important ones our instruction pointer, that's the memory address of the next instruction to be executed. So not the actual code, but the memory address. So naturally, if we want to take over control of this guy, that's something we're definitely interested in. Additionally, since we're doing stack-based stuff, RSP and RBP, because this is 64-bit, so the top RSP is the stack pointer, so that's going to be the top of the current stack frame. The current stack frame is going to be the stack frame of the function that's currently executing. This doesn't make any sense, don't worry, we'll see it actually happen. And again, since the stack is basically upside down, that's going to be the lowest memory address, and RBP is going to be the base, so that's going to be the base of the current stack frame. There are other registers. We don't really have to worry about them at this juncture. We may later. So here's, a very simple, here's main stack frame. These are C programs that we're going to be looking at. So, that's just how C works. When it starts, the first thing to be executed is main. That's the first function, and then it calls other functions. So, high memory, EBP or RBP. Low memory, because again it's upside down, ESP, or in our case RSP. And that's not particularly interesting, but what happens is main's going to call other functions, and when main calls other functions, one thing it's going to need to know is when I finish my function, like this one is called function 1, so after function 1 executes, I'm going to need to know where in main we left off. We don't want to start at the beginning of main again and just have main just loop forever. We want to pick up right where we left off and let main continue seamlessly. So, depending on the architecture, this sort of stuff differs a bit, but ultimately it's kind of the same in the end. But, with our Intel, we have the return address is just pushed to the stack. So it's pushed on top of main stack frame. So at a lower memory address than main stack frame, just right on top of it, the return address will be. So that's, again, going to be a memory address. And that's going to be where in main it needs to pick up. And then function 1 will get its own stack frame. RBP and RSP will move to the boundaries of that stack frame. And again, this is growing to lower memory. So when function 1 finishes, its stack frame gets popped off the stack, and then that return address is loaded into EIP, well, not RIP, which again is the execution. So if we go back up, the instruction pointer. So that's perfect, right? So this address gets loaded in the register that tells it what to execute. So naturally, if we can get control of what's in this return address, the machine will just, magically, just because that's how it works, it will take that address that we control and cause it to execute. So absolutely perfect for exploitation. This isn't by any means the only kind of exploitation there is. There's tons, but I think stack based is a great way to start. And I mean, it's kind of these ideas are kind of the core building blocks for pretty much everything you're gonna do, as you move forward with exploitation. So yeah, again, this one is real similar to the one that's actually in the book. So we have overflow test.c. So for this one, I actually did give you the code. Yay me. That won't be the case in some of the other ones. So if we look at overflow test.c, it's a real simple C function. Well, C program, rather. It's got 3 functions in it. We just include some standard libraries up here at the top. Remember, main executes first, so this is what's going to get executed first. Main, this junk in here, just basically that's how it takes command line arguments. Int argc is how many arguments, and star argv is an array of the command line arguments. So this is going to take command line arguments from the user. The first thing it does is call function 1, and it passes it argv1. So that's going to be the first argument passed by the user. You might say arrays start at 0. Yes, they do, but the name of the program is argument 0. See why off by 1 errors happen. Yeah. And then so it calls function 1. So here's function 1. It takes a character array, str, short for string. It creates a local variable. Remember where local variables go. They go on the stack. So there's going to be room on the stack for that guy. And then it uses a function called strcopy, strcpy, and it just how this works is this is destination and this is source. So it's going to take str, which is passed to function 1, which was argument 1. So it's user controlled input, just like with the web apps and everything else we've seen. User input is generally where things start to go wrong because you can't control it and users might put in things they shouldn't. So there we are. So it's going to copy str into buffer. Buffer's only 5 characters long. So you might imagine what happens if we put more than 5 characters in there. What happens if we put a lot of characters in there? And strcpy is kind of notorious for this reason. It doesn't do any bounds checking. It will happily take 100 characters and put it into 5 characters and just keep writing down the stack. You can see it if we pull this guy up again. I believe I've got again, it's a very crude picture. So if we copied say a lot of A's into buffer, it would continue writing down, because remember it goes down to copy and it grows up, which is the core of the issue really. Again, I wasn't in the room when this happened. So it will copy down to the end of the stack frame. It will do the return address. It will go into main stack frame. You can write off the end of the stack and get an error that way even. Strcopy will just keep doing it. Does that make strcopy a bad function? No, it's a perfectly valid function. But if you're going to use functions like strcopy that don't do any bounds checking, it's up to the programmer to do the bounds checking. I mean, there's nothing to stop the programmer from putting a check in place right here to make sure that str, the user input, is not longer than 5. But they didn't. So there is str in copy with an str in cpy, which does do bounds checking. So it'll have a third argument that is how many characters to copy. and this is certainly not there's a whole family of basically copying strings that doesn't do any bounds checking. So this is just one of them. So that happens, and then we go back to main. Remember, it has the return address saved. So assuming we didn't overflow it, it'll come back to main and pick back up where it left off, and it'll say executed normally to the screen, and that's all it will do. You'll notice that there is a third function up here, overflowed. All it does is print execution hijack to the screen. Under normal circumstances, overflowed is never called. Main starts, function 1 gets called, function 1 finishes, we return to main, we print, and we exit. So our goal for this one is to make overflowed execute. So you can think of this kind of like debugging code that got left in, which does happen from time to time. I mean, I know I do it. So, debugging code that is just never called, but it's still in the program, so it is still loaded in memory. So, it is, for things like data execution prevention and things like that, which I'm kind of getting ahead of myself there. Let's not talk about data execution prevention and ASLR and stuff like that. You have to learn to walk before you can run. I mean, so many people, I think it's like, okay, here, let's go hack the iPhone, when it's one of the hardest platforms to hack ever. You got to have these background bits first. So, this is getting started with exploit development. All right, so, we can just run the overflow test. It's already compiled on here. If I just give it 4 A's, I get executed normally. If I give it like a lot of, well, that doesn't really matter, but if I give it a lot of A's, I get a segmentation fault. So that's an indication that indeed, something went wrong. But we can use a debugger. So the typical one we use on Linux is GDB, the GNU debugger. I mean, there are other ones. There's like WinDebug for Windows. There's, but this is the one we'll use. So we're going to open up overflow test in GDB. And because we do have the source code and the symbols and everything, I make this one kind of super easy compared to the other two, because it is our first, because we can actually, I think it's 16 lines. We can actually see the source code since we have it. And what we're going to do is set some breakpoints first. So I want to see what's going on in the internals of this program, as it runs. And breakpoints allow me to stop execution at a given point. It allows me to look at the contents of memory, the contents of the register, pretty much the state of the program at any given point. So, I want to set a few breakpoints on this guy. So I want to say break, and the first breakpoint I want to set is right before the call to function. So we'll still be in main. So we'll just be able to see what main stack frame looks like, etc. So I'll do a break on line 14. Because we have the source code, we can just call it by line name. You'll see in the future exercises when we don't have the source code, we can do break on memory address, break on all sorts of stuff. GDB usage could be a class in itself. Believe me, I don't even know all the stuff it does. Let's also do a break on line 10. So right before the stir copy, I kind of told you that's the offending function. That's where, if we give it too much user input, we've got, buffer on the stack. It only has 5 spaces. If we give it a lot of stuff, it will keep copying out of it. And that's going to be our problem. So let's put a break at 10 right before the carnage begins. So that will stop the program right before that is executed. And then finally, let's do a third at line 11, right after the stir copy. So right after the disaster. So first, let's just run it normally. Let's run it with 4 A's. You might be asking, why am I doing 4 and not 5? Strings are terminated with null bytes, so just 00 and hex. And so technically, really, we only have 4 spaces because the null byte will happen. Like, the lack of a null byte is what causes a lot of memory leak vulnerabilities, which again is totally out of scope for this, but it will just put a null byte there. So let's run it with 4 A's as the argument. It doesn't put executed normally out to the screen because it's at our breakpoint. Can I do a clear in here without causing problems? Oh, crap. Now I just deleted the breakpoint. Break 10. Right. No break 14. Sorry. My mistake. So now it's going to be breakpoint 2, 3, and 4. Whatever. I'm just trying. I hate that it's like right at the bottom of the screen, but whatever. We'll manage. We always do. Alright, so we can examine memory. So if we do X, which I think is short for examine, and then /16, I'm just kind of guessing with 16, no, it's not a forward slash, it's a backslash, regular slash, yeah, forward slash, like 16 hexadecimal words, and I'm not sure that that's totally the right amount, from RSP. Remember, RSP is the top of main stack frame and should be at the lowest memory address. So over here on the left are the memory addresses, and so they are 16 or wait 8 8 bytes long, not 4 bytes long, because it's a 64-bit machine. That's really the only difference. And if you did this from the book, and then these are the contents of main stack frame. We could see just look at where is RBP. I can't type. So it's at F0, so it looks like, main doesn't do very much. So like this is main stack frame, the contents of it. It is all in hexadecimal, but we're not really that worried about main. I just wanted to see where it was. So if we do a continue, we hit breakpoint 2, which is function 1 has now been called, but stir copy has not happened yet. So we haven't copied our A's in, but we should have a stack frame. So luckily you can do the up arrow on this one. So RSP will now be at the top. It will have moved to the top of function 1 stack frame. So yeah, and we are at a lower memory address. So B is before E. So we've got, and if we do check out where our BP is, it's at D0. So that will be the end of it, because everything's 16-bit. Why do I keep saying 16-bit? Jesus. That was a long time ago. 16-bit happened. Your old video game. 64-bit. So, this is... See, if we remember, E0 at the end was main stack frame. So this is main stack frame. We've got functions 1 stack frame. And then we've got... 8 bytes basically between the two. If we look back at our picture, well, this picture will work. We've got main stack frame, the return address of where to continue in main, and then function 1 stack frame. So that should be, if in fact the theory is correct, that should be that return address sitting on the stack. And we can, if we just do a disassemble main, you don't have to know like a ton of reverse engineering and assembly and stuff for this. I should have changed the flavor. I like the Intel flavor a lot better, but it doesn't matter. So here's the call to function 1 right here. So theoretically at least, the next thing to be executed would be, that address right underneath. If we look here, the reason these things are backwards is because of Indianness. When I was first learning exploit development, Indianness confused me a lot. I've read a bunch of papers about it, and I'm still not entirely sure why there's this debate. I guess they think it's faster. I don't know. But some architectures think that you should load the least significant byte first, and some think that you should load the most significant byte first. The trivia question, this is what I always use to give away books, is where this came from. And actually, it's not people from India or Native Americans. It's Indian with an E, so Endian. And it comes from a Jonathan Swift novel called Gulliver's Travels. One of the places Gulliver travels to is a place called Lilliput. They're having a war with their neighbor about which end of the egg you should crack, the big end or the little end, which, there's bad reasons to have wars, but that's pretty far up there, I guess. So just a little bit of computing trivia. You will probably, if you continue down your exploit development path, run into things that are big Indian, but this is little Indian. A lot of stuff is basically you just need to remember that you need to flip things around byte by byte. So a byte in hex is 2 digits. So everything will be, we'll see it when we get to the point, but basically, yeah, we've got a bunch of zeros, and then we've got 40 058E. So indeed, that looks like that is that return address. So perfect. Well, I mean they're in the right order now, but you'll see. Just I got a little ahead of myself on the Indian this, but when we actually are putting in return addresses, you'll see we'll need to put it in backwards or else. Yeah, that sounds ominous, right? Okay, so it looks like everything actually matches the theory. We've got a stack frame for main, we've got a stack frame for function 1, and we've got a return address between the two. So now if we do a continue, we hit breakpoint 3, which now the stir copy should have executed, so we should still be in main stack, or not main stack frame, function stack frame, function 1 stack frame, and sure enough we are. But if we compare the contents of the two, you see right here we've got 41, 41, 41, and then there's another lone 41 over here. That's another Indian this thing, it's just backwards. So 41 is hexadecimal representation of a big A. I'm not sure who in the creation of exploit development decided we were going to do everything with big A, but a lot of the tutorials, a lot of the proof of concepts will use big A. So if you know one, well, I guess there's two you need to know. Null is 0 0. That's pretty easy to remember. 0 becomes 0 0. Well, it's not actually 0, it's null, but you know what I mean. And big A is 41, big A is 40, or big B is 42, so on and so forth. There's hex tables you can look up. But anyway, so it does look like we have copied some stuff onto our stack frame. It's still, because we only used 4 A's, we're perfectly within scope here. The return address is safe. Because this one is so small, we can actually kind of count like how many A's we need to get to the return address. Because if you remember, our goal is to overwrite this return address with something that we want. But we can count, we've got 4 now, so that would be 5. And then we need 4 more, 9. 4 more is 13. So it looks like we would need basically 13 bytes of padding before we would overwrite the return address, because again our goal is to overwrite the return address, and we want to make it execute that overflowed function, so we'd want to overwrite the return address to send it to the overflowed function. So let's keep going. I get ahead of myself. Continue. So we hit all 3 of our breakpoints and continued through them. It does print out executed normally to the screen because we didn't destroy it. So let's just go ahead and do. Alright, let's go ahead and do this. When I did the book, I was still very much a Perl fan. I'm not as big of a Perl fan. Not that I don't like Perl, but I've become a much more of a Python fan. But, this is how it was done in the book. So, basically you can script inside of GDB. You can give it script input. The reason we want to do this is because we eventually are going to want to use hexadecimal, and if we just do \x and then 0 0, it's going to take that just as 4 characters. But if we do it with a programming language, we can have it actually spit out non-printable characters. And I think it's Perl dash. See, this is why I don't use, I think it's -E for execute. Well, it'll tell me if I'm wrong. So we're saying, so we do the $sign to say basically, execute this before the run. Perl -E for execute. I think that's right. Open what we want to execute, single quote, and I want to print A with double quotes around it. Times in Perl is not a time symbol, it's an X, so A times 13, because that's going to be our padding. Remember we said we needed, we had 4, 5, 9, 13 to get to our return address. And then it's a dot. It's not a plus. It's a dot. Another reason why I like Python better. The syntax just makes a little more sense. So I'm print a times 13 dot for concatenate b x 8. So b times 8. Again, if you're used to doing the one in the book, it would have been b times 4 because it was 32-bit. So our return address was only 4 bytes. Now it's 8. So that's really the difference from the book. Single quote to end your Perl, and close parenthesis. So we're just doing run $, open parenthesis, Perl -e, open single quote to tell it what we want to execute, print a times 13 concatenated with b times 8. So if this works out correctly, we should be padded out with a's with 41s till we hit the return address, and the return address should be filled with our 8 b's. This will likely cause it to crash because, again, b in hex is 42, so it will try to execute whatever's at the memory address, 42, 42, 42, 42, 42, 42, 42, 42. So 842s as the address. That's likely not loaded as a valid address for code. So it'll probably crash, but we'll turn that crash into what we want, which is getting overflowed to execute. Remember, my breakpoint's called 4 because I tried to clear it and it cleared the breakpoint. I was just trying to make the screen go up because, we're typing at the very bottom, it's not very big either. But anyway, so, we can, examine from RSP. Do notice that the location in memory of main stack frame has changed. There are a lot of things that go into where things end up. The length of the arguments is one of them, so that's not surprising that its location has changed. It doesn't matter that its location has changed. The location of code will not change in this case. I mentioned ASLR, or address space layout randomization, as an anti-exploitation defense. There are, in a lot of modern systems, cases where the code location will change, but the location of overflowed, which is what we're after, is not going to change in this case. You don't have to worry about stuff like that yet. You can worry about stuff like that down the road after you've got this stuff down, but you don't have to worry about the stack frames moving. The length of the strings is not going to change. It'll still be the same length. Like if we do check for RSP or RBP. It's at E0, so, we've got main stack frame is still the same as it was. It's the same length as it was. We've got just as much space. The location may change, but yeah, okay. Anyway, all right, let's continue. Nothing really interesting in main. And then we're at our second breakpoint, which is function 1 right before the call to stir copy. So no 41s or 42s yet. There's our memory address of the next location to be executed in main. It hasn't changed. The code, like I said, is still at the same place. So, we could compare that to, up here again from where we saw it before. So same memory address, but if I did my calculations correctly, and this time the calculations were kind of easy. I was just able to go 1, 2, 3, 4. We'll see, with longer strings, obviously that won't be the case. You won't really just be able to do it on site. But, assuming I got that right, I should see a bunch of 41s padding. And then, this third line down at the end, these should be our 8Bs. So let's continue. Now if we examine, sure enough, we've got our lone 41 over here. Our 41s that we saw before, more 41s because now we have 13 41s, and then these last two, which were the return address, are now all covered in 42s. We only gave it 8 Bs, so those are the 8 Bs. Then that should be the exact location where we need our return address to be. If we were off by 1 in either direction, whatever we put there would also be off by 1. So, we wouldn't be able to put overflowed address there unless we got this offset right. Again, like I said, the offset here is 13. We can do it on site, as we'll see in, our next exercises that we'll do where, they're a little bit harder. We don't have the code and we want to run like a shell and things like that. So a bit more advanced. You won't always be able to do this on site. But this one we can. So indeed, if we do a continue, it crashes, gets a segmentation fault. It's trying to execute whatever's at the memory address, 842s. So that's our 8Bs. That's not loaded. There's no code there. It can't execute it, so it crashes. And so now what we can do is put in, so if we do, just like we disassembled main, even though overflowed is never called, it is compiled, it is part of the program. So overflowed is loaded in memory. And so here's the top of overflowed. And let's copy that. And this is where our Indianness comes into play. So if we just go back up to our Perl, so our A times 13 is fine. That's just padding, so we can leave that. But what we want to do is replace our B times 8 with that memory address, basically, which is also 8 bytes, 64 bits, all the stuff you had to learn in the class way back in the day. Computer Science 101. I'll never need to remember this, but then I became an exploit developer, and sure enough I did. So 2 hexadecimal digits is 1 byte. So in order to tell it that it's hex, you do a backslash and X. So if I do just to save myself all those zeros, what I'm gonna do is go ahead and put it in little Indian format. You can do it if you just did it straight. It would come out backwards because this is a little Indian system. There's more about it in the book section. There's more about it on the internet. Basically, the only thing you really need to remember, unless you're taking a test where you have to do a dissertation on what little Indian means, is you want to flip things around byte by byte. So again, 2 digits to make a byte. So my first byte would be the one at the end, which is 37. And then backslash X again, and 05, backslash X again, and 40, backslash X again. So I did 40, 05, 37, and then the rest of them are all 0 zeros, 0 0. So I need to come out with 8 bytes total. So that's 1, 2, 3, 4, 5, 6. And again, between every 2 digits, backslash X, that's just how it works. So what's that? 1, 2, 3, 4, 5, 6, 7, 8. Okay. And be sure to close your double quotes around it. So that's going to print out A times 13, and then the hexadecimal representations of these guys, some of them are going to be unprintable, hence why we need to use, if we just did this run and without the script part, it would see each of these as a single character, whereas we need them to see this is 1 byte, not backslash X 40, it's hexadecimal 40, which, all of our characters have hexadecimal representation. Again, stuff you learned in Computer Science 1, which I promptly forgot and have regretted ever since. Anyway, all right. So again, we did do this backwards byte by byte, not digit by digit. So I didn't do 7 3. I did 3 7. So you just have to remember 2 hex digits makes a byte, and just to do them backwards. Again, you may run into stuff that is big Indian. And if all your bytes start coming out backwards, you've probably forgotten that it was little Indian. So yeah. I'm not going to go into a lot of theory. I hate to think how long this video is already. And just because there's so many zeros, I was like, well, usually when I do the 32-bit one, it's a little shorter and I can do them backwards and have it come out backwards and you can see it. But with all these nulls in there, I was like, I don't know if I'll survive it. And then you guys will all hate me and my typing even more. So anyway, let's run this. Because it crashed, it'll send out, do you want to start the program from the beginning? Because it never exited because it crashed. Just say yes. So why? It's ignoring the null bytes in the input. Null byte is typically terminates a string, so I'm actually kind of surprised that it manages to pull it off anyway. I guess I wrote a good little program. Anyway, you know, we can look at main stack frame, and I don't even think, no, maybe it did move. I don't know. Possibly it moved again, but again, it doesn't really matter. We just did this breakpoint here so I could show you that the theory actually is true. So we can continue. We hit our second breakpoint right before the stir copy. And we've got our same stack frame for function. We've got our same return address here that should take us back to main. If we do continue again, let the magic happen. Now do the examine. You know, we've got our 41s, and then, you know, we've got 40, 0, 5, 37 here. You know, here's our zeros again. Weird Indian stuff. It just, that's one of the reasons that I like to start with 32-bit, is just because it's so much easier to like see the addresses when they're small. But, you know, it is 2020. We should probably just give up on that and just do everything 64-bit to begin with. So I trust that you guys, it mostly made sense. If it didn't totally make sense, we'll do some more exercises. So theoretically, what should happen, you know, function 1 should finish, its stack frame should get ripped off, and it'll load this address in RAP, and that will be what is executed. So it should execute overflowed, or whatever it says, execution hijacked or whatever. So let's see if it does. Sure enough, we do get execution hijacked. It does crash after that. I mean, there are things we could do to stop it from crashing. We'll see when we look at, I mean, we actually did see it already on some of the payloads for Metasploit, like exit functions, for the payload to finish. Basically, you know, I imagine what happens is, because we don't put a return address, it's complicated. Anyway, I mean, but we did execute what we wanted to execute. In this particular case, we did manage to, we killed the program afterwards. Sometimes you're just gonna have to kill the program. I mean, more elegantly would be just to like spawn a new thread and then just kill the thread after, and then have the program keep running. But, I mean, don't worry about the fact that it crashed after. It was never that well of a written program anyway. That was the point. But we did print execution hijacked out to the screen. So that was our goal with this one. So basically we just, you know, did a really simple stack-based buffer overflow here. So we used that stir copy function, the fact that we could give it user input, we gave it more input than was allowed, we overwrote the return address, and we sent it to some, you know, extra debugging function that was still left in the code. So that was the goal for this one. In the next one, we'll make it a little bit harder. One, we're not going to have the code. Two, we're going to, instead of trying to send it to overflowed, we're actually going to use shell code to, you know, make it do other things on our behalf, and there's even a flag we have to get. So again, this is almost an exact replica, aside from it being 64-bit, from the example in the book. So, you know, that's a good place to start. And I will see you guys next time. Let's see how long this video came out. Bye. Oh, 40 minutes.